All right, this is section 1.5. We kind of started discussing the concept of this in 1.4 when we were talking about the tangent and velocity problem. In section 1.5, we're actually going to be talking about the limit of a function. And today we're going to specifically focus on the limit of a function graphically. So let's go ahead and take a look at a specific graph. We're going to graph the function x minus 2 squared plus 1. So to do that, we have to create some tick lines here along the axes. I think going out 6 in every direction should be fine. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Not exactly perfectly spaced there, that's for sure, but we'll do our best. This is just a sketch, but it should do what we need it to do. All right, so the first thing is, hopefully you guys remember from your Algebra 2 and pre-calculus that this thing is a parabola. F of x equals quantity x minus 2 squared plus 1 is a parabola. It's been shifted. It's been shifted 2 units to the right and 1 unit up. So we're going to start by graphing the vertex. 2 units to the right and 1 unit up. There's the vertex. And then I know I can kind of do the rest of this using symmetry. So I can pick a couple of points to the left or to the right of x equals 2, graph those, and then do the symmetric points on the other side to get this parabola graph. So I'm going to pick x equals, let's just go with x equals 3. If x equals 3, you get 1 inside the parentheses. 1 squared is 1, plus 1 more is 2. So when x equals 3, you get y equals 2. And then when x equals 4, plugging a 4 inside the parentheses gives you a 2. 2 squared is 4, plus 1 more is 5. So when I'm at 4, x equals 4, I'm going to be at y equals 5, which is going to be right about there. All right, so now we can just use symmetry. Going to x equals 1 is going to have the same value as x equals 3, and x equals 0 is going to have the same value as x equals 4 since they're symmetric. So that looks pretty good right there. So I'm going to go ahead and sketch my parabola through there. Sketch the parabola going the other direction, and it'll look something like that. All right, so the important part here is as we approach x equals 1, the value of the graph, now the value of a graph is the y value. The value of the graph seems to be approaching 2. Okay, that looks like you can visually see that. And as you can tell, I kind of missed when I sketched my graph, I missed my dot. So the trick is make the dot bigger. There we go. So what we say is the limit of the function f of x equals x minus 2 squared plus 1 as x approaches 1 is equal to 2. Now that's a very long and drawn out way of saying it, but that is technically the way we would say the entire thing. We can shorten that notation to, instead of writing f of x equals the whole function, we'll just use the function itself as f of x. So the notation would be the limit, or LIM, and then below that, x with the arrow to 1 means as x approaches 1, so the x values are going to 1, of the function x minus 2 squared plus 1, you don't have to write the f of x equals there, equals 2. Okay, hopefully that makes sense. Hopefully you can visually see on the graph that when x is approaching 1, the y value of the function is approaching 2. Okay? So we're going to use the same graph to evaluate the following. Let's use the same graph to evaluate the limit as x approaches 2, the limit as x approaches 3, the limit as x approaches 0, and the limit as x approaches negative 1. So let's go back to the graph. The first one is x approaches 2. As x approaches 2 on our graph, so let's see, as x gets closer and closer to 2 on our graph, it looks like the y value here is approaching 1. And again, I'm hoping that you can see this. I'm going to try and sketch this in there. So as x gets closer and closer to 2, So you can kind of see that that's where x is approaching 2 from both sides. The y value is approaching 1, so we can fill that in. Now we look at the graph and say, okay, as x approaches 3. Well, if x is going to approach 3, let's see, when x approaches 3, the y value here looks like it is approaching 2. So we'll fill that in. As x approaches 0, you should be getting the hang of this pretty quickly. As x approaches 0, which is right on the y-axis there, it looks like the y value is approaching 5. So f of the function's limit there, it seems like it's approaching 5. Now the one that's a little bit more tricky, as x approaches -1, if we go back to our graph, I didn't really plot that specific point. It's a little bit harder to see. As x approaches -1, you might have already figured out what you're going to do here. You're just going to plug -1 in for x in this case and then see what that value is, and that's going to tell you what this specific limit is. So if I were to plug -1 into my function, -1 minus 2 is -3. When you square that, you get 9, plus 1 more is 10. So the limit there would be 10. Obviously, it's a little bit more challenging if you're going to approach things like with decimals, like in number 5. So you could use a table of values in your calculator if you wanted to evaluate these things. Or you could just plug 1.5 in and see what you get in this case. Now, obviously, this is not going to work for everything. This is just a starter of what we're doing. So if we were to plug in 1.5, see, 1.5 minus 2 is -0.5. If I square -0.5, I'm going to get a positive 0.25. So if I could take 0.25 and add it to 1, I get 1.25. And again, for things like this, I really do stress mental math. What you see in the chart, not so much. I don't expect you guys to be able to do all of those things really easily in your head. So we're going to go ahead and just use your calculator to double check that you can actually do this. And I will tell you it's very important that you can use your calculator, because there are going to be certain things on the AP test when we get there that you're going to have to use a calculator for. You're just not going to be able to do the problems without it. For the most part, I strongly suggest that you can do these things mentally. Not the stuff in the chart here, that's a little too much. So when I plug in 1.4 into the calculator, if you haven't already done so, you should get a result of 1.36. If I plug in 1.45, I'm going to get 1.3025. If I wrote that correctly, I think I did. And then if I plug in 1.49, I'm going to get 1.2601. 1.2601. Then if I kind of go down to the bottom of the chart and start with 1.6, I'm going to get 1.16. If I do 1.55, I get 1.2025. And then if I do 1.51, I get 1.2401. Okay, and what's important about this is you might be thinking, why am I doing this? Well, if you look at it, if I wanted to find the limit as x approached 1.5, I really want to find out what's happening as the values get closer and closer to 1.5, and I want to find out what's happening coming from both sides. 1.4 is just a little less than 1.5, 1.6 is a little greater than 1.5. And then as I start to get to the middle of the chart, those values get closer and closer and closer to 1.5. 1.49 and 1.51 are much closer to 1.5 than 1.4 and 1.6 are. So really what I'm doing is I'm trying to figure out, what do these things look like they're approaching? Well, we already know what the answer is. It's 1.25. And as you can hopefully see, if you were to kind of average 1.24 and 1.26 or so, you would get approximately 1.25, and that's kind of the goal there. So we're really looking at what is happening to these y values as x gets closer and closer and closer to our desired amount. And you might think to yourself, well, why is this important, especially if I could just plug it in? There are going to be times where that doesn't work, and you can't just plug things in. So we have to have a more analytical way of figuring this out, and that's what we're doing with these number charts here. So in general, we can use the following notation. The notation says the limit as x approaches a, whoops, sorry about that, says the limit as x approaches a of f of x equals L, where L is some number. It's a constant. So the way you say that, once again, I'm going to say it one more time as we go. It's the limit of f of x as x approaches a equals L. And again, for the sake of argument, L is going to be a number. Okay, there are other notations for this, but the one that I just went through is the most common one that we're going to use. There are ways of saying it where you see this notation right down here. F of x approaches L as x approaches A. We will likely not use that notation, but it's there just in case you happen to see it somewhere so you can understand. It's just a different way of writing a limit. The one that we will use is going to be this one right here. The A value is the X value that we're approaching. The L value happens to be the Y value's limit. All right. So here's another example. F of x equals x minus 2 over x squared minus 4. The first question is, when is f of x undefined? Well, we know that f of x is undefined whenever something makes the denominator 0. No matter what happens, if something makes the whole denominator 0, it becomes an undefined value. We can't divide by 0. The whole world will explode and the universe will implode and all that kind of stuff. So when f of x is undefined is whatever values make the denominator 0. So if you look at x squared minus 4, you should hopefully know that there are two values that works for. Obviously, if you plug in 2, 2 squared is 4, 4 minus 4 is 0. But don't forget, if you square negative 2, it also gives you 4. So it's really when x equals 2 and when x equals negative 2. So it's x equals 2 and x equals negative 2. And the real question is, what happens at those points? Something is happening. It's undefined, but what's actually happening there? And there's two different answers to this. When we talk about x equals 2, so x equals 2. Well, if you look at the function at x equals 2, if you plug 2 in, you get 0 in the denominator, but you also get 0 in the numerator. And hopefully you guys remember from your pre-calculus that whenever you get a 0 over a 0, that actually creates a hole in the graph. Okay, and we'll graphically show this because we're going to want to make sure that we see graphically what that looks like. And then at x equals negative 2, because that does not make the numerator 0, but it does make the denominator 0, you end up with a vertical asymptote. All right, so we're going to actually use, in this case, we're going to use a table to figure out what the limit as x approaches 2 is. Now, we know that there's a hole in the graph there. So that means that there's no actual point. There's no y value there. But we're going to actually find that it does have a limit. So if we were to go to our x minus 2 and x squared minus 4 over x squared minus 4 and start plugging in these values, as the x values get closer and closer to 2, as you can see, we're starting with 1.9 and 2.5, which are values which are definitely outside of 2, but then we're going to start getting closer and closer to 2 as we get to the middle. So at 1.9, if you plug that in, you end up with 0.256. At 1.95, we end up with 0.253. And at 1.99, we end up with 0.251. Then if we start at 2.5, we end up with 0.222. At 2.1, I believe it is 0.244. And then at 2.01, after plugging that one in, we get 0.249. And hopefully you can kind of see what those middle two, which are the closest two values that we have to x equals 2, are approaching. Certainly looks to me like if you average those things out, you're going to be somewhere around the neighborhood of 0.25 or 1/4. All right. So there are multiple ways that we could go about sketching this graph. One of the ways would be to literally just start picking a bunch of x values and plugging them in. It's going to really help if we know kind of what this graph looks like. So here's the idea. We can actually simplify the original function. If you hadn't already thought to do that, we can do that. The reason we don't want to completely simplify it first is because you might lose something in translation. So the denominator factors, that's the difference of squares. That's going to be x minus 2, x plus 2. Now what you should be able to pretty clearly see is the x minus 2 and the x on top and the bottom there, those things are going to divide away. So when I write this, I'm not actually going to cross them out. I'm actually just going to divide them away mentally, and I know that that's going to be equivalent to 1 over x plus 2. The reason I don't want to cross those out is because I want to remember that those are the pieces right there that actually give me the whole. So let's go ahead and sketch 1 over x minus 2. Now, this is a graph that if you don't remember what it looks like, we kind of need to know the base function or the parent function of this one. The parent function of 1 over x plus 2 is 1 over x. So 1 over x, or f of x equals 1 over x, basically looks like this. And this is a really rough sketch, but it basically looks like that. Because if you think about it, at 0 you have a vertical asymptote, because if you plug 0 into 1 over x, you get a vertical asymptote right there. Right, 1 over 0 would be a vertical asymptote. And then basically it looks like exactly what you see here. It's basically stuff in the upper right and lower left quadrants there are the values. So if we were to take 1 over x plus 2 by virtue of shifting the graph, really all it's going to do is shift that graph 2 spaces to our left because of the x plus 2. So we're going to shift that graph 2 spaces to the left down here, and I think it's going to make it a little bit easier for us to graph. So I know I'm going to have a vertical asymptote 2 spaces to the left of 0. So x equals negative 2 is going to be my vertical asymptote. Then I know my graph basically looks the same. It's going to look like this, and then it's going to look like this. With one problem of what I did. Remember that in this case, go back up to the original equation, we have a hole when x equals 2. So what I really need to do is kind of erase somewhere around where I think the x equals 2 mark would be, somewhere in that range right there. And I have to over-exaggerate a hole there. So we're going to kind of do this. We put a big open circle that over-exaggerates the hole. Hole should be a little bit higher, probably off the graph. I didn't do it that well because remember that the general idea here is, okay, this is x equals 2. That's when x equals 2. It says that our limit of this thing is 1/4. Well, that means the y values that we found in our chart, as you approach it, as you approach x equals 2 coming from the right, and as you approach x equals 2 coming from the left-hand side, approaches the y value, which is going to be over here, of 0.25, or 1/4. Remember that the circle right there can be opened. The value of the function does not have to exist for a limit to exist. It's what are the y values approaching, not necessarily what the actual y value is. In this case, there isn't one. All right, that's plenty enough for this video. We're going to come back with a second video, and we're going to go through a modified example of this one, as well as define some ways that that the limits can look like, and even ways that limits might not exist.